centripetal forces. According to the Khan Academy definition, a centripetal force is a net force that acts on objects to keep it moving along a circular path. What that means is the inward-facing force that keeps an object moving in a circle. It faces towards the center of that circle as an object rotates around it. And the greater the centripetal force, the smaller the radius of that circle around the center point. The centripetal force, yes, thank you. Centripetal force is perpendicular to the velocity of the object. It's pointing to the center, and therefore the velocity is 90 degrees away from that. A centripetal force is not a fundamental force. It's just a net force. It's all the forces acting towards the center of the circle of motion. So they can be, I've seen additions where it's like the gravitational force and the tension of the string it's rotating on. So it's all the net forces acting towards the center of the circle it's moving around. So the way that works is what provides the centripetal force in a ball and string. It's most likely the tension of the string. When the Earth rotates around the moon orbits, it's the gravitational force. It can also be friction, something that keeps it on a rotating tile or something. That's about it. Do you want to talk about the difference for centrifugal force?
So these two forces are often kind of talked about in the same kind of sentence. So centrifugal and centripetal. But there is a key distinction that has to be made. So centrifugal force is the apparent, and the key word there being apparent, outward force on a rotating mass. So it's sometimes discussed as kind of not being a real force. And whereas centripetal force is what is required to keep an object in rotary motion. So, for example, an example of centrifugal force would be going around on a roundabout and being kind of pulled outwards.
I saw that centrifugal isn't a real thing, but it's only ever useful in describing certain problems. And I saw it's useful when it's the observer of the problem is within the rotating system, like in a roundabout. That's when they can use a centrifugal force to describe it. When they're off to the side, the centrifugal force it isn't useful at all. It's not a force, and you can just not use it at all. Sure. Centripetal acceleration, Will?
Yeah, so this is basically the acceleration of a mass rotating. But when we talk about this, there is no actual change of speed. But because acceleration is a vector, obviously, as you rotate around a center, you change in direction basically as you're moving, and that results in the acceleration because it's changed in direction, and it's acceleration directed in the direction of the path, and it can be calculated with acceleration equals velocity squared over radius.
Yeah, that's kind of useful because for the way to the equations for this, that becomes very useful because we have Newton's second law, F equals ma, otherwise written as A equals F over m. We can substitute the A with v squared over r equals F over m because that's the centripetal acceleration. And then we can move that around a little bit to have the centripetal force equals mv squared over r. So you can see the greater the radius, the lower the centripetal force. Therefore, the greater the force, the lower the radius. Then we can also involve angular velocity, which I don't really understand, to replace v, because v equals the weird W looking sign for angular velocity. So you can have the centripetal force equals m. Equals m r with angular velocity W squared.
It's an omega, Greek letter.
Greek, yes. I also do Greek. Sure. The whole thing about centripetal forces is they're often quite interesting to look at examples of. I have a good one. I have loads of good ones. So I saw, it's again Khan Academy, everything. An example of rotating a ball around a string vertically. So it's a yo-yo trick, but it's just rotating vertically around a midpoint, held on by some string. And the whole point of the problem, you're told the mass and velocity of the rotating thing, and you're told to try and find the tension of the string. So at the top, when it's at the top, centripetal force acting downwards is the net force towards the middle, and that's going to be the tension of the string, obviously just keeping it in, but also gravity, which is acting directly downwards. So the tension of the string is a centripetal force minus the gravity. At the bottom, gravity is acting the other way, so it's only the tension of the string holding it up. So the tension of the string is centripetal force plus gravity, I think. Yeah, basically, so different points, the tension of the string has to be different to hold the centripetal force, which is quite cool. So yeah, lots of weird examples. Do you have any examples?
Well, there's quite an interesting one regarding like a car. So
Yeah.
as you turn like a corner
I
on a
saw this. I saw this and I didn't actually get into it because I saw it was complicated. All right, go ahead.
So yeah, it's a speed of 10 meters per second on a path radius 15 meters. So coefficient of static friction between the tires and the ground for this car to make the turn without slipping is essentially what you have to calculate. So the only force acting in the centripetal direction is the force of the static friction. So v squared over r equals the static friction force over mass. Since and you're expressing the minimum possible coefficient of friction, then for static force is equal to wait, hang on. This okay. This is
I
quite.
did see this and I thought like, oh, static friction. All right, I'm out.
Yeah, this is
Yeah,
a bit.
it's a cool example. It's a cool one to understand because it's obviously like, really important in designing cars, tires, and everything. It's like a very
Yeah.
real world application. I have a cool one. So when it's sort of explaining like a real world phenomenon you might have seen. So when a ball is rotating off a string, again, I love that. I love these examples.
Yeah.
But it's rotating off something like vertically, so it's hanging. There's a thing is hanging off the string and the ball at the bottom. And you see when you like you can rotate it, like move it around, and it's just sort of dangling on the string. So the centripetal force is the horizontal component of the tension of the string. It's moving in a circle, dangling from a string, and the horizontal component of that tension of the string is what is the centripetal force. But also the vertical component of the tension of the string, it has to equal the weight of the ball. So the tension, the vertical component has to be big enough to sustain the weight of the ball, but the horizontal component has to be strong enough for the centripetal force to keep it in circular motion. So if you increase the speed of the ball rotation, so therefore we need a greater centripetal force to keep it like that. We need a greater horizontal component of tension. But the weight of the ball doesn't change. We don't we have to have an equal vertical component of tension. So therefore the ball rotates at a greater angle on the string, have a greater horizontal component but an equal vertical component. That's why if you like if the ball is dangling off the string and you hit it harder, it'll go at a higher angle because it needs to have a greater horizontal component but an equal vertical component for the centripetal force, which is kind of cool. Yes.
Yeah.
Yeah. Nice. Any more examples? Anything else?
Well, I think there is one application that I did find of it. So, a centrifuge, which is obviously it's used to like test like samples. So it's basically it's basically spinning like a spinning
Sure.
circle kind of thing, and it kind of they're rated on their levels of centripetal acceleration, which if you have a high centripetal acceleration, it decreases the time it takes for separation of a sample to occur, and thus the sample to, I guess, be tested for like various things such as.
Just sort of testing the strength.
Yeah.
Yeah.
Well, it's like for testing for like viruses, bacteria, stuff like.
Okay.
I think malaria. They use like centrifuges to test samples.
Cool.
So yeah, that's quite interesting.
Yeah. That's about all I have. Anything
Yeah.
more?
Yeah, same basically.
Cool.